we take a look at the KKT conditions and the strong duality property which holds for some class of convex optimization problems. The KKT conditions, which stand for Karush Kun Tucker conditions. So these are the names of the mathematicians who discovered these. So these are a set of conditions which are equivalent to saying that strong duality holds and optimum x star, lambda star, nu star exist. So let's start like this. So let's assume that we have a problem and we say that x star is the primal optimum, and also we are saying that lambda star, nu star are the dual optimum, and also we are saying that P is equal to D, which is the strong duality, right? So we are assuming these three conditions to hold. So we are assuming that x star exists, lambda star, nu star also exist, and P is equal to D, which means that the primal optimum is equal to the dual optimum. So what does this imply? So we let us start by writing down D. D is equal to G of lambda star comma nu star, and this is written as min over x in calligraphic D, x in the domain, L of x comma lambda star nu star. So far I have not done anything. I have just written down the definition. So this chain of analysis we have already seen, and this is less than equal to L of x star lambda star nu star. So this is less than because of the definition of the minimum. So minimum is always less than equal to any L calculated at any other value, right? So this is definition of minimum. So note that this is equal to f naught of x star plus lambda I star fi of x star plus nu j star hj of x star, summation over j. Now what does it mean for the strong duality to hold? So for the strong duality to hold, it should necessarily hold that f naught of this should be equal to f naught of x star, which means what? This means that this term should vanish, this term should vanish, and this inequality must become a equality, right? So for the strong duality to hold, it is required that these three things hold, right? This inequality must become an equality and these two terms should vanish. Then only strong duality will hold. So these three conditions are basically the KKT conditions, which is, first is primal feasibility, which means we are saying that the x star point is primal feasible, which means that fi of x star is less than equal to 0 and hj of x star is equal to 0, right? So this is very intuitive. We want the optimum point to be feasible. It is a given. And dual feasibility, which is saying that the dual points are feasible, which is also given because lambda I star is the dual optimum, so it is naturally greater than equal to 0. The third condition comes from here. So observe here, for this one to vanish, where lambda I star is greater than equal to 0 and fi of x star is less than equal to 0, this whole term is less than equal to 0. Now for this to be equal to 0, we would require each of these terms in this summation over I to be equal to 0. So this is called the complementary slackness condition. So complementary slackness condition says that lambda I star fi of x star is equal to 0 for I equal to 1 to m, which means that either lambda I star is equal to 0 or fi of x star is equal to 0 or both. So this is called the complementary slackness condition, and it is required because we want to make this term to vanish. This term already vanishes because hj of x star is equal to 0. Right? And the final condition which is required to make this inequality an equality is the stationarity condition. So this condition, there are different ways of writing it. We can write it as x star is equal to arg min over x in calligraphic D of L x lambda star nu star. Right? We can write it like this. So essentially we are saying that x star is the one that attains the minimum if unconstrained, if this D is unconstrained. So in the unconstrained case, we could also say that the gradient with respect to x of L calculated at x star lambda star nu star is equal to 0. So for the unconstrained case, we can also simplify it and say that the gradient is equal to 0. But if it is a constraint problem, then you can generally say it like this. Right? So these are the 4 KKT conditions. And the result that we are saying, let me summarize the result again. We are saying that optimum x star lambda star nu star. So this is the primal dual optimum pair. And then we are saying that strong duality, which is that P equal to D. So if both these hold, then it implies the KKT conditions. And actually there is another result which we will not prove, but which is that these two are actually equivalent, which means that KKT conditions imply that the primal dual optimum pair exists. Right? So this is for convex. For primal dual optimal pair exists and strong duality holds. So KKT conditions imply these two conditions hold for convex optimization problems. In other words, for a convex optimization problem, if you can solve the KKT conditions through some other way, then you would have essentially found the optimum, and strong duality also holds for that problem. Note that convexity does not automatically imply that strong duality holds, or convexity does not automatically imply that KKT point exists. Right? So it is not necessary that these things hold. So for example, let's take a counter example just for you to appreciate this point. So I'm considering the problem min over x square less than equal to 0. It's a trivial problem, and x square less than equal to 0 implies that x equal to 0, so minimum is equal to 0. But let us anyway try to find its dual. So the Lagrangian here is given by L of x comma lambda, which is given by x plus lambda x square. Note that this is a convex problem. The primal problem is convex. Lagrangian is x plus lambda x square. And what is the minimum of the Lagrangian? What is the minimum of x plus lambda x square over all x in R? So what is the minimum of this? We can differentiate and obtain that 2 lambda x equal to 0 or x equal to minus 1 by 2 lambda. So this means that g of lambda is equal to minus 1 by 4 lambda. So please verify this. So here x star is equal to 0 and g of lambda is minus 1 by 4 lambda. So the dual problem is maximum of minus 1 by 4 lambda, lambda greater than equal to 0. And you can appreciate that when we are maximizing a negative quantity, right, it is maximized as lambda tends to infinity, because as lambda tends to infinity, this becomes closer and closer to 0. So that is the maximum possible value that a negative non-positive quantity can take. So in this case, lambda star tends to infinity. In other words, optimal lambda star does not exist. Note that we allowed the functions to take infinity values, but we do not allow variables to take infinite values. So the optimal lambda star does not exist while x star exists here. So this is an example where the lambda star does not exist, although the strong duality does hold. You can verify here that the optimal primal and dual values are actually same, but lambda star does not exist. So there is no KKT point. So for this problem, there is no KKT point. Why is that? So why is there no KKT point? Let's try to find out. Let's try to write down the KKT conditions and let's see what we get. Let's write down the primal feasibility condition, which is that x star square is less than equal to 0, which implies that x star is equal to 0. Then the dual feasibility condition, which is that lambda star is greater than equal to 0. So this is fine. The third is the complementary slackness condition, which is that lambda star times x star is equal to 0. This is also fine because x star is equal to 0. So lambda star greater than 0 is fine. But the fourth condition, which is saying that x star is equal to arg min over x of x plus lambda x square, which is the Lagrangian. So the minimum of this is given by minus 1 over 2 lambda star. So this implies that x star lambda star should be equal to minus 1 by 2, right? And this is directly conflicting with the complementary slackness condition. So in other words, because of this conflict, there is no KKT point because the KKT conditions cannot be solved to give a consistent answer. Right, so this was a counter example where there is no KKT point, and as a result, optimum x lambda star does not exist, or vice versa. The optimal lambda star does not exist, and therefore there is no KKT point. Let us also look at a related theorem, which is the Slater's theorem. So the Slater's theorem says that for convex optimization problems, so let's say that when f0 and fi are convex and there could be affine constraints, and if p star is finite, phi star is the optimum value of the primal objective, so it is finite, which means that it is neither unbounded below nor infeasible, and Slater's condition holds. Slater's condition is that, which is that there exists an x tilde such that fi of x tilde is strictly less than 0 for I equal to 1 to m. So if this strict inequality holds for some x tilde, not necessarily the optimal x tilde, but some x tilde, this strict inequality holds, then these three conditions are equivalent to strong duality, which means that these three conditions imply strong duality. So P equal to D, P star equal to D star, and also actually they also imply that the optimal lambda star is bounded. So the norm of the optimal lambda star is bounded by something which is finite. Okay, so this is called the Slater's theorem. So Slater's theorem is very useful in determining what convex optimization problems will have strong duality. So all you need to do is make sure that the problem is feasible and not unbounded below, and the functions are convex, and that there exists some x tilde such that strict feasibility condition holds. Then you can conclude from there that strong duality holds, and therefore you can use the properties Note that when confirming strong duality, you only need to worry about nonlinear constraints. So if there are linear constraints, you don't have to check their strict feasibility. So strict feasibility is not required for the linear constraints. It is only required for the nonlinear ones. Actually, if you go back and check this example that we were seeing, observe in this problem that Slater's condition does not hold. Right? I hope it can be seen here that the Slater's condition does not hold because there does not exist any x tilde such that x tilde square is strictly less than 0. So this is not possible. Hence, in other words, you could say that Slater's condition does not hold in this case. So before concluding, let us look at a simple example of KKT conditions, and later on we will look at a more complicated example. So let us consider min over x half of x transpose px plus q transpose x subject to ax equal to b, and let us say that p is positive semi-definite. So what kind of problem is this? You can observe that since p is positive semi-definite, the objective is convex. There are no nonlinear constraints, so fi's are not there, only affine equalities are there. So this is also fine. Therefore, this is a convex optimization problem. And since as long as this is feasible, so for feasibility, we require that B should belong to range space of A, right? So let's say that this condition also holds, which allows us to conclude that this is feasible and P is positive semi-definite. Then in that case, as long as the solution of this is not unbounded below, the Slater's condition is satisfied and therefore strong duality holds. And a byproduct of the fact that strong duality holds is that you can then solve this problem by finding out the KKT points. Also, in this case, we can directly solve the KKT conditions. So let us write down the KKT conditions. The first is the primal feasibility, which says that if x star is the optimal point, then ax star is equal to b. That is the primal feasibility. There is no lambda here because there are no inequality constraints. So we don't have to write down the dual feasibility condition. Then the third is the complementary slackness, which again is not required here because there are no inequality constraints. And then the final is the stationarity condition, which is simply saying that x star is the optimum of the Lagrangian. Or in other words, let us write down the Lagrangian. So Lagrangian is given by x comma nu equal to half x transpose px plus q transpose x plus nu transpose ax minus b. So the derivative of this with respect to x should be equal to 0. So in other words, we obtain that p times x star plus q plus a transpose nu star is equal to 0. Hence, these are the two KKT conditions, and if we can solve these, then we would have found the KKT point, right? And that would correspond to the primal dual optimal pair because this problem, for this problem, strong duality holds. So let us see what it means to solve these two. Note that x star, let's say, is a vector in Rn, and let's say nu star is a vector in Rm. Then this is a system of how many equations? There are m equations here and there are n equations here. And there are also m plus n number of variables. Hence, what you can see here is that you can solve this two set of equations as by writing them as P A transpose A0 x star nu star is equal to minus q and b. So this is the system of equations corresponding to the KKT conditions. So for quadratic problems with linear or affine constraints, you can see that the solving or finding a KKT points or a KKT point amounts to solving this system of linear equations. And as soon as you solve, you have the primal optimal, which is x star, and also the dual optimum, which is nu star. Right? So this is a simple scenario where KKT conditions can be directly solved and the primal dual optimum pair can be obtained. So in general, that may not always be possible because KKT conditions themselves may be nonlinear equations and may not be easy to solve, but it is in fact possible when you have a quadratic problem.